Welcome to the next session. Now we start the session with classroom workbook from question number 87. Go through classroom workbook. Let us start the session with question number 87. Let C be a circle defined by x square plus y square equal to 9. Oriented positively. That is, the direction of the curve is anti-clockwise direction. Then 1 by pi into integral 3y minus e power cos x square dx plus 7x plus square root of y power 4 plus 11 dy over c equal to blank. So we need to find out this line integral. Now when you look at this line integral, it is in the form integral p dx plus q dy. Now this is actually 1 by pi into integral p dx plus q dy over c. Now what is p value? This is p value 3y minus e power x square, and q is this 7x plus square root of y power 4 plus 11. Now let us apply Green's theorem. So by Green's theorem, this line integral becomes 1 by pi into double integral dou q by dou x minus dou p by dou y dx dy over c. Therefore, this is 1 by pi into double integral dou q by dou x. Now dou q by dou x is 7 minus dou p by dou y is 3. So double integral 7 minus 3 dx dy over c. This is 1 by pi into, anyhow this is constant, so this is 4 by pi into double integral dx dy over c. So this is 4 by pi into area of the curve C. What is the curve C? It is a circle. So therefore this is 4 pi into the area of a circle is pi r square. Here r square is 9. This is the equation of a circle, r square is 9. Therefore this quantity is 4 into r square is 9. Therefore this is 36. Therefore simply it is based on Green's theorem. Okay, write down this calculation. It is a vector u bar equal to minus 2y I bar plus 2x j bar. Evaluate the line integral I equal to integral u bar dot dr bar over c, where c is the closed loop formed by connecting the points 1, 1, 3, 1, 3, 2 and 1, 2 in that order. So here what is C? C is a closed loop obtained by connecting the points 1, 1, 3, 1, 3, 2 and 1, 2 in that order. What is u bar? Minus 2y I bar plus 2x j bar. So then the value of I is, so we need to find this line integral. This is the general form of a line integral. Here C is given that a closed loop formed by joining all the points in that order. Now let us call these points as A, for example B, for example C, D. Now therefore I need to find line this. So the, for example, point A is this. This is 1, 1. Now 1 to B. 1, 1 to B. This is 3, 1. Next B to C. This is 3, 2. Next C to D. So this point is 1, 2, like this. So first find the line integral from A to B in this direction. Next to B to C, closed loop. Next to C to D, again D to A. So we have started from A, again it must end at A. It is a closed loop. So assume that this line integral is obtained by taking all the 4 points. That means this is I1, for example. This is, for example, I2. In this direction this is I3 and in this direction this is I4. That means let us find this line integral along I1. So this is I2, this is I3, this is I4. So the first line integral I call it as I1. This is along this path I2. Along this path the line integral is I3. Along the D to A, the line integral is I4. Therefore, here the integral I is nothing but I1 plus I2 plus I3 plus I4. Now let us find I1, I2, I3, I4 individually. So therefore here I1 is actual line integral. This is integral U bar dot dr bar. So from A to B, this is from A to B. So I1 is a line integral along a curve joining the points A to B. Now you can see here it is given only in terms of I and j. K bar component is not given. This is integral U1 dx plus U2 dy or A to B. Now this is integral U1 dx. Now you can see this is a minus 2y dx plus U2. This is 2x dy from A to B. Now along A to B, when you look at this, the value of y is 1. Y value 1, y value 1. Y is not changing. It is 1, 1. But x is changing from 1 to 3. Y value is constant. So along A to B, x changes from 1 to 3 and y equal to constant. This implies dy must be 0. Difference in y is 0 because y is a constant. Therefore, this line integral I1 becomes integral. Here y value is 1. So replace y value 1. So this is minus 2 dx. But dy is 0. So therefore, x limits are from 1 to 3. So therefore, this is minus 2 times integral 1 dx is x. Limits are from 1 to 3. Therefore, this is minus 4. So therefore, the first integral, that is line integral I1 is minus 4. Similarly, you can find like this. In the direction BC, x value is 3. But y value is ranging from 1 to 2. So in that case, x is 3 means dx is 0. But y changes from 1 to 2. Similarly, when you go in this direction, so x is ranging from 3 to 1. But y value is 2, fixed, just like this. From D to A, x value is 1, fixed. So y value is ranging from 2 to 1. This is just I1 only, okay? In the similar way, I can easily find I2, I3, I4, and my final line integral will be sum of all these line integrals. Got this point? So first work out I1. Now let us find second integral I2. So here I2 is integral U bar dot dr bar from B to C. Now along B to C, the value of x is 3, but y varies from 1 to 2. Therefore, this I2 becomes integral U2 bar dr bar B to C. So therefore, this is from B to C. But here x is 3. X is 3 means dx becomes 0. So you will not find this quantity. So this becomes 2x dy. But what is y value? Y value is 1 to 2. Y is ranging from 1 to 2, but x value is 3. Therefore, in this case, y value is ranging from 1 to 2. Just 1 to 2. X is 3. So replace x by 3. So this is integral 1 to 2, 6 dy. So therefore, this is 6 into integral y 1 to 2. So this one is 6. Therefore, the value of I2 is 6. Now let us find I3. So I3 is integral U bar dot dr bar from C to D. Now from C to D, in this direction, x is ranging from 3 to 1. But y value is 2, fixed. So in this case, y value is 2, but x changes from 3 to 1. So therefore, this I3 equal to, anyhow y value is 2, therefore this dy becomes 0. So this is just integral U1 dx only, but x1 is ranging from X is ranging from 3 to 1. Now therefore, what is U1? This is 3 to 1. U1 is this 2x. So let us write the U1. What is U1? U1 is minus 2y and U2 equal to 2x. So here U1 is minus 2y. This is minus 2y dx. But y value is 2. Therefore, this is integral 3 to 1. Y value is 2. So, therefore, this is minus 4 dx. Therefore, minus 4 into integral 1 dx is x. Limits are from 3 to 1. So, therefore, this becomes 8. So, 1 minus 3 minus 2, this is 8. So, I3 equal to 8. So, note down I2 and I3. After this, we can go for I4. Now, let us find I4. So, that means it is a line integral where it is a line joining from D to A. So, this is from D to A. Along D to A, what is x value? X value is 1. But y is ranging from 2 to 1. Y varies from 2 to 1. So here x value is 1. Therefore, let us find I4. This I4 is integral u bar to dr bar from D to A. From D to A. Therefore, this is integral u1 dx plus u2 dy from D to A. Now here x value is 1. So dx becomes 0. So therefore, this becomes integral u2 dy, but y is ranging from 2 to 1. What is u2 value? U2 value is 2x. So therefore, this is 2 to 1. U2 value is 2x. This is dy. But what is x value? It is 1. So integral 2 to 1. This is 1 dy. This is 2 dy. Therefore, this value becomes 2 times y. This is from 2 to 1. So 2 into 1 minus 2. Therefore, the value of this is exactly minus 2. Therefore, here I4 equal to minus 2. Therefore, the final integral I equal to I1 plus I2 plus I3 plus I4. Minus 4 plus 6, 2. 2 minus 2 will get cancelled. Therefore, this is 8. So, the final line integral is 8. When you look at this, it seems to be very complicated. So, just we have found out this line integral along A to B and from B to C and from C to D and at last from D to A. So, in this case, 4 line integrals are required. But when you look at this, it is a rectangle. What is the length of this? So, the length is 2 here. Length value is 2. What is the breadth value? You can see here breadth value is 1. Length is 2 and breadth value is 1. So, it is a rectangle. This closed curve C is a rectangle. Length value is 2. The distance is 2. You can see here it is 1. Here it is 1. Length value is 2. So, length is 2, breadth is 2. Therefore, this is a rectangle. Opposite sides are equal. So, you can easily calculate this like this by using Green's theorem. When you apply Green's theorem, this becomes integral u1 dx plus u2 dy over the curve C equal to double integral dou u2 by dou x minus dou u1 by dou y dx dy over the curve C. So therefore, double integral dou u2 by dou x. This is dou by dou x of 2x. This is 2 minus dou u1 by dou y. This is minus 2 dx dy. So this is over C. So 4 into area of C. So therefore 4 into what is area of a rectangle? Length into breadth value. 2 times 1. Therefore this is 4 times 2. This is 8. Therefore this problem can be handled very easily by using Green's theorem. And that is complicated way, but try to understand that and this. This is the most simplest way to solve this question. Just by using Green's theorem. In both the cases, the result is 8 and here it is 8. So note down even this calculation also, right? Classroom work is over. If at all there are some more good questions, we can go for line integral, at least one more question. Otherwise, it is not required. Now let us move to the next concept, that is surface integral. Now let us see what are the parameters required to define a surface integral. Suppose f bar is a vector. This is a vector. And n bar is a unit normal vector to the surface S. N bar is a unit normal vector to the surface S of a 3D curve, of a three-dimensional curve. So here we were discussing two important points. One is f bar and another is a unit normal vector to the surface S of a 3D cube. So basically this S is nothing but surface of a three-dimensional curve. Most probably it will be surface of a sphere or surface of a hemisphere, or it will be surface of a three-dimensional cube. Cube is nothing but three-dimensional. Sphere, extension of circle over three dimension. Hemisphere, right? So therefore here three quantities will define a surface integral. What are they? The first one is vector f bar. This is my general vector, and there is some surface S of a three-dimensional curve, that is we call it as S, and there is a unit normal vector n bar to that surface S. Now let us see, suppose this is the surface of a 3D curve. Therefore in this case this is S, so draw a perpendicular vector n bar. So normal vector means perpendicular vector. So it must make 90 degrees with the surface of this. Now draw the tangent. This is nothing but a tangent to S, tangent to the surface S. So S is surface of a 3D curve and its a tangent is like this. So draw one perpendicular vector, unit normal vector to the surface S, and f bar is normal vector. In that case, the double integral f bar dot n bar ds, double integral f bar dot n bar ds over S. This we can call it as surface integral of f bar over S. This we can call it as surface integral of f bar over the curve C or over the surface S. So f bar is normal vector, S is surface of a 3D curve, and n bar is a unit normal vector to the surface S. Suppose I have a 3D cube. So draw one perpendicular vector, unit vector. Unit vector means length is 1. So draw one perpendicular vector whose length is 1, which is a tangent to the surface of a 3D curve. In that case, this defines a surface integral of f bar over the surface S. Now let us see how to evaluate this double integral. So basically surface integral is a double integral. This is a dot product. This is my original vector. This is a three-dimensional curve, surface of a 3D curve, and this is a unit normal vector to the surface S. Now this can be handled by using one famous result, that is called Gauss divergence theorem. Now let us see what it indicates. It connects a triple integral and a surface integral. Therefore, double integral f bar dot n bar ds over the surface S. This is given by triple integral divergence f bar dv over S. So therefore, this is the connection between a surface integral and a volume integral. Surface integral and a volume integral just by finding divergence of this vector. Okay. So very famous result. At first, let us write the definition of a surface integral, standard form. Let f bar be any vector. Let f bar be any vector. Let f bar be any vector, and n bar be a unit normal vector, and n bar be a unit normal vector to the surface S, and n bar be a unit normal vector to the surface S of a 3D curve. Let f bar be any vector and n bar be a unit normal vector to the surface S of a 3D curve. Then double integral f bar dot n bar ds double integral f bar dot n bar ds over s is called surface integral of f bar over s is called surface integral of f bar over the surface s. So always remember that this is the standard form of a surface integral. Next, write this Gauss divergence theorem. Statement of Gauss divergence theorem. Very, very powerful. Next one, Stokes theorem. Now basically Stokes theorem is a theorem which connects two types of integrals. One is a line integral and another one is a surface integral. Let us see the connection among line and surface integral. This is the general form of a line integral. Integral f bar dot dr bar over c. Standard form of a line integral. Integral f bar dot dr bar over c. This becomes surface integral by replacing f bar with its curl. So therefore this is double integral called f bar dot n bar ds over s. Now this is the relation between a line integral and a surface integral if C is boundary of the surface S. C is boundary of the surface S. This is the connection among line and surface integrals. Just replace f bar by curl f bar. This is a dot product and even this is also dot product. So replace f bar by curl f bar. So in this case the curve C becomes S, because when you discuss surface integral, surface of a 3D curve is required. When you discuss a line integral, some general curve is required. So what is the connection between C and S? This is the line integral, it becomes surface integral. And f bar becomes curl f bar. This curve C becomes S. So this is true when C is a boundary of surface S. See the magic? When you look at Gauss divergence theorem, there is a connection from surface integral to volume integral. But in case of Stokes theorem, there is a connection among a line integral and a surface integral. But do not combine these two results. Generally, people may think that Stokes theorem states a connection between line integral and a surface integral. Gauss divergence theorem indicates a connection between a surface integral and volume integral. So when you combine these two, people may expect there is again a connection among line and volume integrals. Don't expect this. Okay. So this is simply Gauss divergence theorem is a theorem which connects a surface integral and a volume integral. But in this case, Stokes theorem represents a connection among a line integral and a surface integral. So note this point. Now let us start classroom workbook based on Gauss divergence theorem. Let us start with question number 89. The surface integral double integral 1 by pi into 9x I bar minus 3y z bar dot n bar ds over the sphere S given by x square plus y square plus z square equal to 9 is blank. So we need to find this surface integral. This is in the form double integral f bar dot n bar ds over S. So what is the value of this surface integral? Now let us apply Gauss divergence theorem. By Gauss divergence theorem, this becomes that is double integral f bar dot n bar ds over s. This becomes a triple integral by replacing f bar with divergence. So triple integral divergence f bar dv over s. Now you can call it as this as f bar. So already 1 by pi is there. Therefore this is 1 by pi into. So divergence of this vector. What is my vector f bar? F bar is 9x I bar minus 3y z bar. Now the divergence of this vector is 6. The divergence of this vector is 6 because this is dou by dou x of 9x plus dou by dou y of minus 3y. So this is 9 minus 3, it is 6. So luckily we got divergence, a constant expression. So therefore this is 1 by pi into divergence is 6. 6 into dv over s. Therefore 6 by pi into this is volume of s. So therefore this is 6 by pi into what is volume of a sphere is 4 by 3 into pi r cube. So pi gets cancelled. This is 8 into what is radius? Radius is 3 because this is 3 square. So therefore this is r value. So therefore this is 8 into 3 cube. So therefore 8 into 27. So this is nothing but 216. Therefore when you apply Gauss divergence theorem, we were getting directly a constant 216. Simple application of Gauss divergence theorem. This is my f bar. This is very important model. Frequently they were asking questions on this model, and interestingly in almost all cases the divergence of this vector is some constant, and most of the cases, more than 90% cases, the surface S is sphere, rarely it is a cube. Okay, so by applying Gauss divergence theorem, this surface integral becomes a volume integral like this. Here this is my f bar. Of course 1 by pi is there extra, so the divergence of this vector is 6. This is 1 by pi into 6 by pi into volume of S. Volume of a sphere is 4 by 3 into pi r cube. In this case radius is 3. So when you simplify this, we are getting 216. Note this. Next we move to question number 90. Here vector v bar is given like this. X into cos square y I bar plus x square into e power x j bar plus z sin square y k bar. This is my vector v bar. X cos square y I bar plus x square e power x j bar plus z sin square y k bar. And S is the surface of a unit cube with one corner at the origin and the edges parallel to the coordinates axis. That means here S is nothing but a unit cube. That means in a cube all sides are equal. So here all sides equal to 1. When you look at the cube structure, so it will be like this. So all sides are equal to 1. All sides are equal to 1. Now in that case, we need to find double integral v bar dot n bar ds over s. So by Gauss divergence theorem, this becomes triple integral divergence v bar dv over s. When you find the divergence of this, so this is triple integral dou by dou x of x cos square y, or I can find divergence v separately. So here divergence v bar equal to dou by dou x of I bar component. This is x cos square y plus dou by dou y of x square e power x plus dou by dou z of z sin square y. So therefore this is cos square y, this is 0 plus sin square y. So therefore this is 1. Therefore this becomes triple integral 1 dv over s. So this is volume of s. So it is unit cube, all sides are equal to 1. Along x-axis 1, along y-axis 1, along z-axis 1. So volume is 1 into 1 into 1. So therefore this is volume of s equal to side whole cube. So it is 1. Therefore, the final surface integral is 1. Let's discuss last question. This is 91. Given that f bar equal to x square minus 2y I bar minus 4yz j bar plus 4xz square k bar. So the value of line integral f bar dot dr bar over c along the straight line c from 0, 0, 0 to 1, 1, 1. So we need to find out this line integral. Options are given. So what is my curve? What is my vector function? X square minus 2y minus 4yz plus 4xz square, where C is a straight line segment joining the points 0, 0, 0 to 1, 1, 1. Now in this case, when you look at this, this is point P1, this is point P2. When you are evaluating line integral over C, if C is a line joining of 2 points, what we need to do is, we need to find curl of this vector. So curl f bar equal to, this is I bar, j bar, k bar, partial derivatives dou by dou x, dou by dou y, dou by dou z. So I bar component x square minus 2y, this is minus 4yz, and this is 4xz square. So suddenly when you simplify this, you won't get null vector. Now this is quite interesting. In the previous sessions when we handled questions like this, when you are handling line integrals, when C is a line joining of 2 points, we got directly called f bar equal to null vector. In that case, f bar equal to grad pi, and based on that pi value, the final integral is pi of P2 minus pi of P1. But interestingly, in this case, called f bar equal to null vector, it is not a null vector, therefore you cannot apply fundamental theorem. Now how to handle this? So this can be handled like this. Here when you look at C as a line joining of 2 points, the points are very flexible. Those points are 0, 0, 1 to 1, 1, 1. That means x is ranging from 0 to 1, y is ranging from 0 to 1, z is ranging from 0 to 1. So I can go for parameterization. X value t, y value t, z value t, and limits of t are 0 to 1. So in this case, the points are very flexible to apply parameterization for this curve. X is ranging from 0 to 1, y is ranging from 0 to 1, z is ranging from 0 to 1. So limits of t are 0 to 1. Now it is parameterization. Therefore, this line integral f bar dot dr bar over c becomes integral 0 to 1 f bar of r of t dot product r dash of t dt. So you know how to handle this. Okay. So you continue this. You will get the final answer as this is minus 1. As the session is very coming very soon, so I am closing this. But you can verify this, you will get minus 1. Just parameterization. Okay. This is very interesting. Note this point. At least you note these points, you can handle later also.